Now the solution is done. So we will see the velocity and temperature contour, and we will post process the data. So first of all, let's see the velocity contour. So go to graphics and animation, go to contour, and here select the velocity, select the field and display. Then you will see the velocity distribution. You can change the level of our color display, and you can also reposition your color map from left side to the bottom. And you can also change the, so as you can see here very clearly, this is your inlet. So you have a very high velocity at the inlet, and as it goes in the wall you have no slip boundary conditions. So you have minimum velocity at the wall and maximum velocity at the center line. You can clearly see that. If you want to see the vector, then you will see the distribution. So select the vector, velocity, magnitude, display. So this is the vector. You can scale it a little bit, and then you can skip so that you can see the different velocity distribution. Here you can see the velocity distribution very clearly. So this is the velocity distribution, and this is the velocity vector. If you want to see the temperature contour, go to temperature, static temperature display. Then you will see the temperature contour here. So at the inlet you have very high temperature, but as it goes through the outlet you can see the temperature of the liquid is reducing. As you can see, as you can go more and more, here you can see the more temperature is reducing along the center line. So it would be very interesting to see the plot along different horizontal direction of the tube. So we will do that. So let's plot some velocity distribution. So go here and create the lines. So if you go here in the drawing module, you can see this is our origin. So this is the origin, this is the 0 point, and if we want vertical line in the x direction, we need to change the x coordinate and y coordinate. So for horizontal direction, our x coordinate will be same for both this point and this point, only the change will be the y. So let's say we want a line every inch apart for first 5 line. So let's create line. First line is 1 inch apart, so our x1, x0 will be 1, x1 will be 1, y0 is 1, and y1 will be 1 inch, because 1 inch is the diameter, that's the height. So but before we do that, here the dimension is meter. So first change the dimension from meter to inch. So go to general, unit, go to length, and from meter change to inch and close. Now go to plot, xy plot, new surface, line. Now you can see the line in inch. So first x1 y1 is 10, x0 y0 is 10, and x1 is 1, y1 is 1. So this is line 1. Create. Now change the x value. This is line 2. Create. Change the x value. This is line 3. Create. Change the x value. This is line 4. And this is line 5. So we have created 5 lines. If you want to see the lines, go to graphics and animation, go to mesh, setup and display, and you will see the mesh. So zoom it and then go to outline and display the outlines. Now select line 1. This is your line 1, line 2, line 3, line 4 and line 5. So we will see the velocity distribution along this line for different position. So let's do that. So go to plot, XY plot, setup, change the variable. We want to see velocity magnitude at line 1, plot. Then you will see a single line. The problem is the direction vector. So you change the direction vector from 0 to 1, plot. Now you can see the velocity distribution. It's look like the velocity distribution here. So it's developing. So if you want to see more precisely, you can rotate this plot. So go to position, Y position, plot. Now you change the variable from velocity. Now you can see the velocity at 1 inch distance from the origin. Now line 2, select line 2 and plot. Now you can see the distribution for line 3. It's getting more parabolic. Line 4 and line 5. So you can easily see the change of velocity. That's here. Here is the developing velocity and here is a fully developed. We can easily observe here also at 1 inch apart the velocity is the white one, and at 2 inch apart the velocity is the red one. So it still is in developing velocity, but at 3 inch it's getting more parabolic. If you want to see more precisely, go here, axis, and uncheck the auto range and see between this velocity and this velocity, that is 0.015 to 0.025. So change it to 0.015 to 0.0225. Apply and plot. Now you can see more precisely. So here the velocity at 1 inch is developing, at 2 inch also developing, but at 3 inch is fully developed. So we can see the entry length is more or less 3 inch for this tube and for this velocity. But if you see the temperature distribution, so go to temperature and select line 1, plot. Then it will show you the error because we choose the range. So check the auto range, apply, and then plot. Then you will see the temperature. So this is also a developing temperature distribution. Line 2 is the same, line 3, line 4, line 5. So the thermal boundary layer is, in general, the thermal boundary layer is much higher than the velocity boundary layer. So we will create more line, but not in 1 inch apart. We will create lines 5 inch apart. So go to line and change it to 10 and name it line 10, so 10 inch apart. And we will create another line 15 inch apart, so name it line 15. We will create 20 inch apart, 20, name it 20, and 25. So we have created 5 line again, 5 inch, 10 inch, 15 inch, 20 inch, and 25 inch apart. So each line is 5 inch from each other. So now we will see the thermal boundary layer. So first select line at 5 inch, so plot. So this is at 5 inch. Now select the 10 inch and plot. So still it's developing, but it's getting more parabolic. So select line 15. Now you can see it's getting a shape more parabolic. Line 25, still in developing process. So we'll create another line 30, create, and let's see. So now you can see at line 30 you have almost the parabolic temperature distribution. So we can say the thermal entry length is still developing. So by this process you can see the boundary layer for velocity, the momentum boundary layer, and the thermal boundary layer, and you can see the temperature distribution along this tube. And we can also see the heat transfer. So select the heat transfer. In the wall compute, you have 1.8 kilowatt of heat is being transferred from your inside liquid to outside wall. That's why it's negative heat transfer. And you can also find the surface heat transfer coefficient. If you go here, area weighted average, go to wall flux and surface heat transfer coefficient, select the wall and compute. Then you will get the surface heat transfer coefficient 223 watt per meter square Kelvin. So you will get these numbers according to our problem setup. You can change the liquid, you can change the material, you can change the dimension, or you can change the boundary condition, and you can design with this preliminary design tool. You can also model the heater based on this internal flow. In the next tutorial we will see the 3D simulation for the same problem. Thank you.